Okay, so I'm going to go over number 2 for the conservation of momentum notes worksheet. That's the one with the running bowling ball on it. So for number 2, a red car is driving at 15 meters per second when she rear ends a green car that is moving only 10 meters per second. The red car has a mass of 1,200 kilograms and the green car has a mass of 1,050 kilograms when they get stuck together during the 0.4 second collision. So first thing to notice is that they are getting stuck together during the collision. And what that means is that they are both going to have the same velocity then after the collision. And so that's why you're going to have two bar charts now where we can have both cars as one object because they are both going to be moving at the same speed. Before the collision, however, we have the red car that was going faster and has more mass. Because it's going forwards, it's going to be positive. And the green car is also going forwards. The green car has a mass of 1,050, and its initial speed is 10 meters per second. So you're going to have a smaller momentum. And then just remember that this is a momentum bar chart. So when you're doing this, this is the momentum of the red car and the momentum of the green car. It's not the mass, it's the momentum. So that means that we need to actually do mass times velocity to figure out how big these are. And in part B, it asks us for those momentums. So I'm going to go ahead and do that. So the momentum of the red car is going to be equal to the mass of the red car times the velocity of the red car. So here we have the momentum of the red car is going to be equal to the mass of the red car times the velocity of the red car. And so we were given the mass of the red car and the velocity of the red car. So that's where we're getting those numbers from. And so that means that my momentum here is going to be 18,000. And then the units are kilograms times meters per second. And for the momentum of the green car, we have the mass of the green car, which was 1,050, times the velocity of the green car, which was 10. So then we will have the momentum of the green car is 10,500. So now what we need to do is we need to do our momentum bar charts. So just as a comment here, this one now we know is 18,000. And our green one is 10,500. So they're not perfectly drawn to scale, but that's fine. And then what we're going to do is after the collision, we need to know how much momentum there is. Well, if you remember, when we add before the collision together, the momentums before, it has to be equal to after. And so if I have 18,000 and I have 10,500, that means that these two are going to have to add together. So if I look at this bar, I'm going to have this much for the red car, and then I need to add to it this much for the green car. And so that'll be my total momentum after the collision. And so because I know how much each of these boxes are, I can then figure out my total momentum. Okay. Now the same thing is going to be true for this other one, but this other one on the right-hand side here, this is going to be if you think about the red car and the green car as two separate objects. So I have my red car and I have my green car, and then after they smack into each other, I still have a red car and a green car. I just don't know how fast they're going. And so one of these might get a little bit bigger, one of them might get a little bit smaller. So I know that the red car is going to have to slow down a little bit when it gets stuck together. And that means that the green car is going to speed up a little bit, but that doesn't mean that they're going to have the same momentum. In fact, they will definitely not have the same momentum because they have different masses and they're going to be going the same speed. So these are not the same height. They're closer together, but they're not the same. So the next thing it says to do is using the momentum bar chart, write an equation for this situation. Put V for the velocities of the two cars after the collision. Okay, so the way that you do this is I'm actually going to write it on the bar chart and then I'm just going to move it down to part C. So the momentum of the red car plus the momentum of the green car, because that's what I've drawn here, is going to be equal to the momentum of both cars together. So that'll be of the red car and the green car. So this will be the momentum of both cars together when they're stuck together. All right, now the same thing is true for the other equation. And I could just do the same thing. So I have my momentum of the red car plus the momentum of my green car, because the left side's the same. And that's going to be equal to the momentum of these two cars. So again, it's going to be momentum of the red car plus momentum of the green car. Now, what gets tricky is once you've done this, each momentum is actually going to be mass times velocity. So I could also write each of these as mass times velocity. So mass of the red car times velocity of the red car plus the mass of the green car times velocity of the green car equals mass of the red car times velocity of the red car. And we have plus the mass of the green car times velocity of the green car. All right, now, when you do this, you know from the beginning of this that these are getting stuck together. So these two velocities are actually going to be the same. So instead of writing them like that, I'm just going to write them as velocity v, because they are the same velocity. And then what I'm going to do is, this is my equation. And then when I go to solve it, I'm going to put in numbers. And so I'm going to go ahead and start putting in numbers to this. And the mass of my red car is 1200. Mass of my green car was 1050. And then the velocity of my red car initially was 15. And the velocity of my green car initially was 10. And I've already actually calculated these momentums up here in the previous part, so I could even just put these in. This is going to be 10,500, and the red one is going to be 18,000. Now, on the right-hand side, some of you are going to get stuck here. Just remember that this is very similar to if I had done, let's say, 2x plus 3x, that'll be equal to 5x. Well, it's the same thing. It's just v's instead. So 1200v plus 1050v will give me a total of 2250 times v. And if I add these two together, I get 28,500 is equal to 2,250 times my velocity. And then to solve, I just need to do the opposite of multiplication, which is division. So I divide both sides by 2250, and I get 12.66 repeating is my velocity. And so that is the answer for part D. Alrighty, so for part D, we just got our final velocity. Now this is the final velocity for both the green car and the red car, because both cars are stuck together. So it's as if here's my red car, and both cars are moving along at the same speed because they are stuck together. So I originally had a red car that was going 15 meters per second, and now it's going 12.66. So to find the change in velocity, I just need to do final minus initial. So I have 12.66 repeating minus my original speed, which was 15 meters per second. And so that gets me a change in velocity of 2.33 repeating meters per second. And then for the green car, I do exactly the same thing. So I'm also doing final minus initial, and it was also going 2.66 repeating meters per second originally. And now it's going, and initially it was going 10 meters per second. And so it has a difference of 2.66 meters per second. Cool. All right, so for the last part, it says, how much force did the cars push on each other with during the 0.4 second collision? Well, you already know that from the first problem that your change in momentum is equal to force times time, or your impulse. Um, but we don't have the change in momentum for this one. So instead of using change in momentum, we're going to remember that the change in momentum is equal to mass times how much your velocity changes, because the mass of the car is not changing during the collision. So if I put this in for my change in momentum, I get mass times my change in velocity is equal to force times time. So when we use this equation, we either need to use the mass of the red car times the change in velocity of the red car, or we can do the mass of the green car times the change in velocity of the green car. And it doesn't matter which one we do. The only thing that matters is that whatever mass we use, we have to use that car's change in velocity. So the mass of the red car is 1200 times the velocity of the red car, which is negative 2.33 meters per second. And that'll be equal to our force times the time of impact, which is only 0.4 seconds. So I go ahead and I divide both sides by 0.4, and I get a force of 7,000. Now you might notice that this negative needed to go there. And that's okay if you give me a positive or a negative force. That just tells me the direction that the force is going. And then I'm going to go ahead and plug in the numbers for the green car. All right, so you divide both sides by 0.4 and you will get 7,000. So this might be interesting because the forces are exactly the same. And actually, you do know that that is true because any two objects that push on each other will always push on each other for exactly the same amount of time with exactly the same amount of force. So if you have any questions, let me know.